Hello, so welcome back to our channel, and we are here to present you another linear IC voltage regulator and how we can design this circuit. On your screen, you can see the schematic of this linear voltage regulator. And here you see we have described the theory of this regulator in detail. And in that category, we said that this is a configuration of standard IC voltage regulator. So what you see here, we have this input voltage source, and that is having some voltage which is unregulated voltage source or power supply. And then I explained to you in theory that, okay, this is our pass transistor or a power transistor structure. This is your power transistor that essentially provides you the required load current IL that flows through your load. So let's say your load current requirement is about 1 ampere, and that is how the standard regulators are used for when you have a requirement of delivering a large amount of load current. So approximately 1 ampere or large load current. So, and then we explained that this transistor Q2 provides the current to this Darlington pair composed of two NPN transistor, and to this PNP transistor we had this another transistor that provides a supply to this PNP transistor. Okay, so this is an NPN transistor that provides supply to this PNP, and this PNP provides supply to the Darlington pair. So we saw that there was the feedback loop. You sense the output at this node basically, and you use a simple voltage division circuit composed of two resistor R1 and R2, and the middle of that voltage which is sensed is given to an error amplifier which is drawn right here. So you see here is a net A that is connected at this node. So negative input, this is a simply operational amplifier. Negative input of it is connected to the node A, and another input, that is positive input, is connected to the reference voltage. This is a fixed voltage that comes to the circuit from some external supply. So objective here is to explain you the working of this circuit, and we are going to simulate this circuit step by step. We'll run the DC analysis, we'll run the operating point analysis where we will see all the voltages and the currents. So here is your unregulated power source, and finally here you will have the output voltage. So this error amplifier output right here, this is the net, which is the output of the error amplifier, is connected to the base of this NPN transistor. And finally, the collector current of this transistor is being given to this PNP transistor. Okay. Now we know that the linear IC voltage regulator, and one type of it is a typical IC voltage regulator as shown in the figure, is also called as standard IC voltage regulators. There is a dropout voltage, which is the differential voltage between V in and the V out, is about 2 volt to 3 volt. So you can have this flexibility to drop this much of the voltage across the regulator before you can, without the circuit coming out of the regulation. Here are your power supply rails, that is positive rail and the negative rail that is supplying power to your operational amplifier, which acts as an error amplifier. Error amplifier will simply have two voltages at the positive and the negative input, and based on that it will generate the positive potential or the negative potential, which will be driving this transistor Q4. Okay, and subsequently it will drive and control the load current. Error amplifier, as we know, it's simply output voltage is zero when the two voltages at the positive and the negative inputs are same. Otherwise, it generates the positive voltage or negative voltage based on that. So let us understand step by step how this circuit will work. We will select the design values of the component. For example, we know that the current flowing through the R1 and R2, which is I, is kept to the very low value so that the maximum current is your load current that can be supplied to the load. So we'll see that step by step. Okay. Now the output expression is given as V out is equal to V reference in bracket 1 plus R1 over R2. So clearly the reference voltage multiplied by the ratio of the two resistor plus 1 sets the output voltage of this circuit. So depending on the values we will choose. For example, here it is 10K each. So for example, V out will be 2.5 volt. Remember, this is our 2.5 volt here in bracket 1 plus 1 divided. So it will be about 5 volts. So we want, let's say, a 5 volt at the load current of, let's say, 0.5 milliampere, or let's say, 0.5 milliampere will be this too low. Rather, we would say we want the current is about 0.5 ampere. So that's our current requirement for a given load. Okay, so let me write it here properly. Let me write here. It will be like, yeah, here it will be over 0.5 ampere. So now we will investigate and explain how we have chosen the components, their specifications from the library. You can use any spice for your schematic drawing and for the simulation, but the important is to understand the analysis. So for example, I would like to tell you about the transistor parameters. There are two parameters are important, that is IC in milliampere and the VCE, that is the voltage, open circuit voltage of the transistors. And the dropout voltage VD, which is like differential V in minus V out. And this is how our drop on voltage will be. So if you want a 5 volt at the output, your input should be 2 or 3 volts greater than the input voltage. So I have chosen here 6 volts, so it would not be sufficient to maintain the regulation. So let us select it to be 10 volt. Let me change that in a moment. So if you see here, if you right click this transistor, I have chosen a transistor which is 2N3019 from this manufacturer. It is a NPN transistor which has an open circuit voltage across its collector to emitter about 80 volt. Okay, if you can click pick new transistor, here you will see a library of variety of transistors. So I have chosen this model 2N3019. You can see from the SPICE syntax or the model, it has number and NPN, and there is like beta factor 200 is the gain. And look at here, I have chosen the IC is a milliampere. Maximum current it can supply is 1 ampere for the open circuit voltage of 80 volts. So that's why I chose this, because we want, that's why we call it as a power transistor. Second transistor is the same I have chosen because this is one single composite transistor, PAR transistor, which is providing the current. Now you see this transistor, I right click and you see this is the number, this is the manufacturer, and the collector current it can supply is about 500 milliamp, and for the open circuit voltage between collector and emitter 45 volt. Then this transistor, that is Q4, if you right click this, you see this is able to supply maximum collector current of 100 milliamp for the 45 volt across its collector to emitter. Now I just explained to you this should be required, whatever the required voltage is, it should be few volts higher than. So let's keep it like 10 volt. And with that done, the resistors, the current through this voltage division should be chosen in a such a way that there is a minimum current flows through those resistors to reduce the power consumption, overall power consumption within the circuit, so that the current goes through the load. So I have chosen the values about 10K each, or let us have it for example 20K each, 20K or even 50K, so that your current will be maximum, let's say 50 kilo ohm here and 50 kilo ohm here. So I'm not going to explain you how I pick up these components from the library and how I pick up this operational amplifier. If you right click the operational amplifier, it is the universal model of the amplifier I have taken from the SPICE directory, and I defined these parameters as per my requirement. I chose the open loop gain to be about 1 into 10 to the power 6. The gain with product of this amplifier is 10 mega, and the offset voltage is 0. So it's pretty flexible to choose such parameter. The supply voltages for this op amp is 10 volt and minus 10 volt. So because that's the dual power supply I have chosen. Okay. So we are all set to understand how this circuit is going to provide us the voltages and the currents. So circuit will work like this. You have input current coming from this supply, let's say I. The rest of the circuitry will draw this current supplied by this unregulated bar source. And this current is then splitted into the PNP transistor, like the emitter of it, the base of it, right here, and which is also the collector of this NPN. Then you have a collector current, right? And it will flow, it will become the base current of this NPN transistor, which is a part of Darlington pair. This is your emitter again, and this is your collector. So here your IC, and here your IE. Then this current goes ahead right here, which is the collector current of this NPN transistor. And finally, you have this emitter right here, the IE. Then that is splitted further into these two parts. That is I, which is flowing through R1 and R2. And then you have this load current that is coming finally to the load. Okay, so this is how. Now looking at the error amplifier, you have this voltage net that is labeled as A. Reference voltage is set to 2.5 volt. The positive and the negative rail is the supply. And we have defined the universal error amplifier, universal op amp. We have defined some parameter like how much gain we want, how much gain with bandwidth product. Gain with bandwidth product is defining the speed of your circuit. So essentially it is a DC circuit. So you don't need a high speed amplifiers. Gain bandwidth product about 10 mega is sufficient. And refer to the previous videos about the working principles of all these things. So what happens is that the voltage here at the node A is fed back to error amplifier. The two voltages uh, uh, are compared. Actually, if the voltage, there is no voltage difference, output of the error amplifier is zero, and there is no signal, control signal to this transistor, and subsequently the load is maintained to the constant voltage. The output is maintained to the constant voltage. However, there is a variation either in the load or in the fluctuations in the supply. You have the error voltage generated, which is given to this transistor, and load current subsequently is controlled. So we have seen this explanation in the previous module. So refer to that. Now here I am going to compute the operating points here and show you various voltages and the currents and optimize the design accordingly. Okay. So what we will do here, we click the simulate and then click edit simulation command. And here we have variety of analysis to be done. So we'll select DC operating, which will compute the DC operating point. Here is the syntax. As soon as you select that, .op, click OK, place somewhere on the schematic, and that's it. So let us run, click here, and see all the voltages and the currents into the circuit. So rather to see it wisely, let me just remove all the drawings on the screen, and here you are with the voltages and the currents. So your input voltage, as you can see, is the 10 volt, which is the regulated voltage right here. Then your output voltage is 5 volt. So as expected, we just designed this power supply for the 5 volt. Then you have voltage at the node A, which is 2.5 volts. So before that, let me show you by right clicking on the net, how you can see the negative input of the op-amp or error amplifier is connected to this node. Similarly, I told you the error amplifier output is connected to the base of this transistor. So just right click on the net and click highlight, you will see the connection between the nets. Coming back to the analysis again, we are running the operating point analysis, and the node voltage at the, you can see that these are the supply voltages for the operational amplifier. The output of the error amplifier is set to be 0.26 volt. That is a constant voltage. If there is a difference voltage coming, then you will have some changes in the output voltage here. So we'll see now how these things are taking place. Now the collector current of the transistor Q1, which is this transistor, is providing you about 0.005 ampere. So 5 milliampere, and the base current is given, collector current is given. So similarly, these are the all three currents for the transistors there. Now the current through the resistor R1 is 50 microampere. So you see it's pretty less current we intentionally made to flow through the R1 and R2. That is how it is. Now the supply current is about 5 milliampere. That is your current. Reference current, this is the current through the voltage source V3. Where is the V3? Let me check. V3 is and V4 are your power supplies to the op-amp. So we'll not talk about that. So that's it. So you have like these kind of things. Now, if you have a load is like 1K, it's quite big. What about we choose rather 0. Or let's say 200 ohm. That's the load we have. So with that, we'll run the analysis again. And now you see you have input 10 unregulated, you have V out 5 volt as expected. And then you have, these are the supply voltages, V plus and V minus. Output of the error amplifier is 0.3 volt. And collector current of the transistor is 24 milliampere, and that is how we want to see that. So let me see that how much is the collector current. So this is like 24 milliampere you are supplying to the load actually. And current through resistors is also given here. And what about I of V1? So that's your supply current. That is about 25 milliampere. Okay. Now what analysis we can do? We'll see if there are some changes in the load, or if the output voltage remains constant or not. So we need to run the analysis for that. So right click here, rather say, put the curly bracket, let's say X, and that's it. So we'll run the step analysis to simulate the behavior of the circuit for varying load. So we'll do that in a moment. So what we do here, we come to Spice directive, click here, and we'll just do the stepping. We'll write the syntax dot step param, and it is X, and take the values from, let's say, 100 to 200, or let's say 500, and maybe just not too much. Let's say 100 to 200 at the step of 10. It will see the value of the registers from 100 to 200 ohm at the step of this one, and we'll see how much it goes. So we'll click OK, and that's it. The command is done. We'll tile the windows, and now you see your schematic is there. So what you want is plot the output because the waveform has appeared. So see the probe on the schematic, click output, and you have a constant voltage all the way right here. Okay, zoom to fit. Let me do some changes here. We'll do some more things. For example, let's say a 10 to, let's say, a 5K is about, yeah. So we'll do that. Save it, run it. We'll see that. So here it is. So you see, for the very low value of the value of a resistor below 100 ohm, your output is really dropping, right? But after that, for a very low value of load current, it is maintaining pretty constant output regulation. But from if your load resistance is a very low value, it means when you are required to deliver a large amount of current, then the output of this regulator is having such a huge variation, but it is still close. Output is varying just like 2% to 5%. The minimum is, let's say, 5.00004 to 5.00025. So you can just see the change in percentage. Okay. So for this kind of circuit analysis, you are seeing how the output voltage is available. What about there is a variations in the input, for example, okay, some input fluctuations is there. So let us do that, try how it will function. So we'll keep the load voltage fixed, let's say about 100 ohm. That's the one, and you want to disable it. So right click, and what you do is just have this symbol from your keypad. You actually have the comma. Yeah. So when you see this kind of symbol, then your command is disabled. Now, what we want is to sweep this one, DC voltage source. So we'll click simulate, edit simulation command, and we'll go for a DC sweep. Which source you want to sweep? Name of it. So it is V1, type of sweep linear, start value. So let's say it is 5 volt, and or maybe 10 volt, what we are at, and the stop value go down. So let's say about 5 volt. Increment is 1 volt. Click here, place it somewhere, and then simulate. That's it. Now you see input stepping down from 10 volt to 5 volt, and then come back to schematic, click output. Look at this output voltage. When your input is falling, the green curve from 10 volt down to 8 volt something, the output is still 5 volt, blue curve down. Very good regulation. However, the input continues to fall. You have fall in the output because circuit is out of regulation. That's it. And then the output is 0 for very low values of the inputs. And the output voltages can be as high, input voltages can be as high as possible. For example, you step it from 20 volt, run again. So no problem by maintaining that. So here is the importance of the maintaining the overdrive voltage, which is a differential between input and output. Okay, so you got that correct. Close the window, make it maximize. Now disable this command again, .dc, and put that sign again. You disabled it, and you enable it. Remove this here. So your load is varying from, let's say, 10 to 100 at the increment of 10. For example, this is how you will do that, right? Fine. And sweep again. Operating point analysis. See, automatically it got disabled. Again, you have to put it. So you have it already, so it's not taking it. Cut it, and then press escape on the keypad, right click, remove this symbol and make it enable here. Then click run. It's operate asking you that again. I made a mistake. You need to choose the parenthesis again, X right here. And that's all, because that's the parameter you're sweeping. So here we are done with the operating point. Click the output, and you understand now for the different values. The output starts from 5 volt and then it drops to 0.5 volt for the values of the load. But then after this value, your resistance, load resistance 50 ohm minimum, you have a constant voltage output. So better go for this one. Okay. What about your net list or your file? Okay, so edit simulation is done. View, you have like spice error log. Click here and you see here all the voltages and the currents, all the parameters of the BJT that you have used for this circuit. Okay, now there is one more analysis we can do here. That is the step analysis. So we'll do that.